3D rotations. Okay, now we've lived in the world of 2D, and 2D, nothing is really 2D, everything is 3D, right? So this is probably going to be an extension of what we've done so far. So what we've seen so far is I drew a lot of figures like this: x0, y0, and then there's a new frame, x1, y1, and then I'm intentionally going to call this angle here as psi. Okay. Now, I said that this rotation matrix is basically relating frame 1 with frame 0. So I had this rotation R10 as cosine psi minus sine psi, sine psi, cosine psi. Okay. But really what this is actually rotation about the z-axis. The z-axis is something you do not see here. I've not really showed it, but it's really pointing out of the plane of the paper, right? So when you, so let me just draw it here first before I use it. So it's, think of the z-axis pointing out. Then we have x0, y0. So this is clearly z0. And when you're doing this psi rotation, what you're doing, in fact, is you can take your right hand, point your thumb in the direction of z0, and curl your fingers, and that is basically how the c is defined, or the psi is defined. So curl your fingers to rotate x0 to x1. This is psi, and then this would be y. And then when you do that, you'll see that your z-axis remains same, right? Doesn't change. So z0 is z1. So again, if you want to figure out psi, take your right hand, point your thumb in the direction of z0, turn the vector, make your fingers along x0 and turn them, and then that turn, the rotation, is basically how much psi has how x0 has moved to x1, and that basically defines the angle traced by psi. Okay, so this is what you actually did, and one way of representing this in 3D world, so this is the 2D world, is to have a 3x3 matrix instead of a 2x2 matrix. Cosine psi minus sine psi, sine psi, cosine psi, 0, 0, 0, 0, 1. Okay, that 1 indicates that the z-axis is unaffected. z0 is the same as z1. Okay, but we really don't show it in 2D motion because we don't really look at motions in the z direction. But here we will, because we will look at rotations which will be in z, along x, along y, and so on. So what I'll call this matrix is now R. It's a function of psi, but its rotation about the z-axis, so I'll put a z there. Okay, so this is my 3D rotation versus 2D. It has the same form as a 2D rotation, except for that 0, 0, 1, which I added. Now, similarly, you could do the same thing for x and y. So I'll show you rotations about the x-axis and the y-axis, similar to this. The rotation about the y-axis would be, so there will be a 1 sitting right, row 1, row 2, column 2. That is indicative of the y-axis being not rotated, and then you'll move the thetas over here, cosine theta, sine theta, minus sine theta, cos theta. And then there will be a rotation about the x-axis. Let's have that parameterized by phi. So again, you'll put 1, 0, 0. This is because the x-axis is unchanged because of the rotation about the x-axis. and then we'll put cosine phi minus sine phi, sine phi, cosine phi. Okay, so now one thing to remember is this is not an error. Okay, it looks very different from this formula or from the previous one. You see, it's minus is over there, and then the minus is here, but here the minus is down. That is not an error. That is how it is. Okay. Rotation matrix. Okay. Now this is just rotation about one axis, but what if you had two rotations or three rotations about three axes? So in general, you can write a rotation matrix as follows. R21, R22, R23, R31, R32, R33. Okay. Clearly, these are 9 numbers, right? 9 elements in the rotation matrix. But what really a rotation matrix represents is basically rotation about the three axes. Rotation about x, y, z, or you could also have x, y, x. So we really don't need 9 numbers to represent a rotation matrix. Okay. So how is that possible? Well, it turns out that a rotation matrix like the one I showed here is constrained in certain fashion, and those constraints come because of the properties of a rotation matrix. One of the property of the rotation matrix is that R transpose R should be I. So certain properties restrict the range values that R's in the rotation matrix take on. Okay. So these properties are R transpose R is I. You could also write it as R transpose is I, where I is a 3 by 3 identity matrix. This property, R transpose R equals I, is actually the property that these rotations are orthogonal. Well, sorry, this don't, my bad. This is not orthogonal. This is the scale to 1. That is, a rotation matrix when multiplied with a vector should not change the length of the vector. Okay, so that property that the scale is 1, that is the magnitude of R is 1, is basically encompassed in this. Okay, and this actually encompassed in the diagonal elements. That is, in the diagonal element of R transpose R, you see there's I. That means that the row, when the property that R when multiplied with a vector will not change its magnitude, is basically in the diagonal element. And then the off diagonal elements, which is the orthogonality, is encompassed in non-diagonal elements, which means that these rotations are so chosen that they actually form a 90 degrees or orthogonal set. Now I can expand this and write these equations as follows. So this is just taking R matrix the way I wrote it down with those R11, R12, and so on, and I get the following conditions. Okay, and then the other property is that you need to do summation Ri1 Ri2, where I will go from 1 to I will be 1 to 3 should be 0. This is saying that the vectors or the R's are orthogonal to each other. So this comes out to, if you expand this out, you'll get R11, R12 plus R21, R22, R3 plus R31, R32 equals 0. And then there's similar for the other two. So Ri2, Ri3 equals 0, where I will go from 1 to 3. Then I want to expand that out. Ri3, Ri1 equals 0. So I will go from 1 to 3. And this is the other property, orthogonality of rotation matrix. Okay, so these are 3 conditions, and these are 3 conditions. Orthogonality and unit magnitude. And so what we have here is, if you go back, I said, well, there are 9 numbers which describe a rotation matrix. Well, these 9 numbers are not free. They are constrained. They're constrained by this six conditions, 3 for unit magnitude, 3 for orthogonality. So the free parameters, there are 9 parameters. There are 6 conditions, which leaves you with 3 free parameters. So rotation matrix is described only by 3 unique numbers, 3 free parameters or 3 unique numbers. Okay. So one way in which these 3 free parameters are written for your rotation matrix is known as the Euler angles. So it's a very, very common thing. If you talk about rotations, you'll hear Euler angles a lot of times. So these 3 unique numbers are given by Euler angles. So we'll talk about Euler angles fairly in detail in this part of the course. So let's see what Euler angles are. It's basically describing rotation matrices with angles, and those angles can have there are various conventions of describing Euler angles. So there are actually 12 ways of doing that. Euler angles. Okay, so you can have rotation about x, then y, then z. So this is describing rotation of any object in 3D space can be written as rotation about x followed by rotation about y followed by rotation about z. You could also reverse this. You could keep the x constant, reverse the z and y, which is also a valid set. You could also do x, yx, or x, zx. These are all valid rotations. You don't have to have x, y, z coming in the combination. You can do x, y, and x. That'd still be unique. You can't have x, x, y, because then that x and x doesn't really make sense, because you can just add the 2 up to x, x, and that'll be 1 rotations. And if you have that 1 and then y, you won't have 3 unique numbers. You could also do this about y. So y, x, z. Keep y constant, reverse the last two. You could do y, x, y, y, z, y. You could do z, x, y, z, y, x, z, y, z, and z, y, sorry, z, x, z. So these are 4, 4, and 4. And so if you add all them up, there are 12 unique ways of describing rotations. Now, not all of them are used, right? It's similar to how you use language, right? A particular object might have 10 names in a language, in English or Spanish or whichever language, but there's a convention where you probably use one name, not all the names. So some of these feature, so some of them have a name, some of them feature in some specific application. So if you go to aerospace, they will use this convention. It's called Tate-Bryan, and it's used in aerospace engineering. These ones, X, Y, Z, are known as, you commonly we'll come across as 1, 2, 3 convention because it's the X, Y, Z, and they're known as Bryant angles. Okay, so what we'll do is we'll actually stick with ZYX. We'll use this in our class. This is a 3 to 1, that is ZYX 3 to 1. We will use these in the course. Okay, so there are different ways of representing rotations. They ultimately represent the same thing, but it's just a different convention. Just like you could call an apple as something in English, and you can call same thing in Spanish, Portuguese. They have the same different names, but they represent the same entity. Similarly, these rotations represent the same thing, except that you have a different way or naming convention to describe rotations. Okay, so that is what we'll use. 3, 2, 1. Now, before I actually start using it, there's something which is kind of very important. This is where 2-dimension rotations are different from 3-dimension rotations. And this is actually kind of, this is what makes rotations in 3D much harder than 2-dimensional rotations. So in 2D, rotations commute. Okay, what I mean by that is, if you, let's do this, which we have done in the past, X, Y, Z. So you rotate about the Z-axis, let's say θ1. Then you do another rotation. So it's θ1. Now the second rotation, let's say, is θ2. So you end up with what? θ1 plus θ2. Now you could reverse this rotation. You could just start off with θ2. And then do θ1. I think I should have shown this a little smaller. This is θ1 is slightly less than theta. Okay, let's call it θ2. And now do θ1. This whole thing is θ1 plus θ2. And it's really obvious that it's the same thing, right? So the order is not important. order of rotation is not important in 2D. That is, rotations, this implies rotations commute. So rotations do commute in 2D, but they do not commute in 3D. And I'll actually show this to you, just prove it to you. So typically how this is done is, if you remember, if you want to do a rotation, R, the net rotation is R. First you do θ1, then you do θ2. And in this case, you do theta 2, then you do θ1. The net rotation is θ1 plus θ2. You get the same thing if you do it this way, θ1 plus θ2, irrespective of how it was done, right? θ1 first, so θ2 first, then θ1. Okay, this is just the rotation matrix, a 2x2 matrix. If you do the multiplication, you'll see that the net result is θ1 plus θ2. That is to say that they do commute. The rotations in 3D do not commute. Rotations in 3D do not commute. Okay, let me show this to you. Actually, a good demonstration. Here is an object which has different dimensions in the x, y, z direction. Okay, and so I'm holding it this way, and the convention I'm going to stick to is that x is this way, y is to the left, and x cross y is z, so it points up. So x, y, and z is up. X cross y is z. Okay, now what we'll do is we'll carry out two rotations. First is 90 degrees about x, then 90 degrees about y. We'll note the position of the object, then we'll reverse it. We'll do 90 about y first, then 90 degrees about x, and then we'll note the orientation of the object and see that those orientations are different. Okay, so let's do it slowly. Again, x, y, z. First, we'll do 90 degrees about x. So x is this way, and I need to do 90 degrees about x. So I take my right hand, point my thumb towards x, and then turn by 90 degrees. So when I do that, it becomes like this. So first remember that there's a del here, it's pointing up. So when I turn this 90 degrees, go this way. Okay, so that's 90 degrees about x. So remember the x-axis remains unchanged. Now the new y-axis is this way. The y-axis will remain the same direction as it is with the objects, this way. So I turn about 90 degrees about y now. So I take my thumb, point it along y, turn by 90 degrees about the y, and so it'll end up this way. So you can see the del now, it's facing you. Okay, I started with del up, and now the del, the symbol here, faces towards you. So 90x, 90y. Let's do it the opposite way. So again, x forward, y left, z up. First, let's do 90 degrees about y. This is y. So I point my thumb this direction. I turn by 90 degrees. So this way. Okay. Now, x is pointing downwards. Y is this way. Z is up this way. So I turn 90 degrees about the x. This is x. And I need to point my thumb in the direction of x and turn it this way. So I turn it this way. And so you see that the del, which was facing you earlier, now is facing this way. So this is just showing that when you do 90-degree rotations, just 90 degrees, but you could do other ones, that rotations do not commute in 3 dimensions. Okay, we'll carry out this once more so that's easy to understand. So x, y, z, 90 degrees about x this way, 90 degrees about y this way, and so this del is facing you. Start again with del up, 90 degrees about y. This is y, like this. Then x is here, 90 degrees about x, and del is pointing this way. So rotations do not. Yes, so let's carry out these rotations now. in sequence. So 90 degrees about x-axis. So point your thumb towards x and turn the whole thing about the x-axis. So then what will happen is you'll end up with this configuration. With x still pointing this way. Okay, the frame y rotates with the object, so it will be in the same direction as it was originally, and then z would be this way. Now let's do the second rotation, 90 degrees about y-axis. Okay, so point your thumb along y and then turn it about 90 degrees. So this is the thumb of your right hand. And so if you do that, then you end up with y still pointing up. Z would be this way. X would be in this fashion. And that's about it. Now let's do the reverse way. So start with 90 degrees about y, about y-axis. So it's point your the thumb of your right hand along y-axis and turn it by 90 degrees. So this will look like this. Y will still be this way. This is y. X is down. And z will be this way. And then let's do the last set, which is 90 degrees about x-axis. Okay, so point your thumb, the thumb of your right hand along the x-axis and turn by 90 degrees. That is, your fingers are curled in that direction. So if you do that, this face will be like so. X is still down. My bad. This is not that right. So when you do this, this face, the biggest face, the one with the largest area will be facing the other way. So it'll be, this will be the way the face is. So let me draw it like this. The biggest face is pointing the way I've shown, and then green, Y, Z. So we can see that this configuration is, this is the final configuration. The one on top is not the same as the configuration down. And that's because these rotations do not commute in 3 dimensions. What I should put here is 90 degrees about x. So this is 90 degrees about x. This is 90 degrees about x. And then 90 degrees about y. And 90 degrees about y. It's obviously easier to show by doing the demo than to show it on this. But I actually also have, if it's easier for you, I also have code which will do this, and you can check it much better than what I did with my pen. Here is some code which will do the same thing. This just shows the same idea, commutativity. Okay, so here we have the same thing shown using Python. So you start with the same configuration on top. The first one does 90 degrees about x, then 90 degrees about y. So 90 degrees about x. So the x is this. So it's the red will remain unchanged. And then 90 degrees about y. So the y will remain unchanged. The y is the green unchanged. And then you do the opposite way. Start with the same configuration as this one, then do 90 degrees about y, followed by 90 degrees about x. And so you see that this configuration is not the same as that configuration. So you have not. Yes, as I said, this is the 3 represents rotation about the z-axis first, followed by rotation about the y-axis, then about the x-axis. Okay, so if you want to visualize this, really don't need to, but let me just put it down in case you think that helps you. So what I would do is I would draw x, y, z. Okay, first is rotation about the z-axis, and that's, let's say that the rotation angle is psi. So again, point your thumb in the direction of the z-axis and use the curled fingers as the means to figure out how much is the rotation. So here the z-axis would be unaffected, but it would turn by some angle in the xy plane. So this would be a new x, this would be new y, and your psi is what we're going to use is this angle. Okay, so see that z is remaining unaffected. That's always a property of the way the rotations are. You rotate about z-axis, that axis will remain unaffected. Now, next what you do is we'll do a rotation about the new y-axis. So I'll need to redraw this figure with the new y-axis, y prime, new x-axis, x prime, and the z is unaffected. Now, it looks a little weird here, but here it's basically in still the angles between z, y prime, x prime is 90 degrees. Okay, so there's a plane formed by x and y, x prime and y prime. Next, we rotate about the y-axis. So again, curl your fingers of your right hand along y prime, and point the thumb in the direction of y prime and curl your fingers along the arrow I've shown, and that would give you a new. So it will be rotating along the new new y prime axis, and it will be in the zx plane. So this will give you something like this. Okay. This would be x prime, c prime. This is obviously the z, not change. Well, actually, I call them z double prime because the second rotation. And this angle, we'll call that theta. Okay, and finally, we'll do the third rotation. Okay, so now we'll rotate about the new x-axis. That's the last one. So I need to redraw this figure with x double prime, z double prime, and y prime. And since rotation about the x prime, I take my right hand, point my thumb against x double prime, and curl my fingers along the arrows shown. And let's say that I get So it'll move in the YZ plane. So it will be new Y. This will be the new Z. This is my new Y. I'll call that triple prime because it's the third rotation, Z triple prime. And this angle is phi. Okay, so let's see what's going on. Say if you have a position vector C0, it undergoes a rotation to C1 in the first transformation. Then it goes from C1 to C2 in the second transformation. Then it goes from C2 to C3 in the third transformation. So what I would like to be able to do is to write these transformations using rotation matrices. So C0 is R. The first rotation was about the Z-axis, this one. So R, Z, and that angle we chose was psi. So this is just saying that it's rotation about the Z-axis parameterized by the angle psi, and that will get me to C1. Then C1 will go a transformation about the Y-axis, the second one. That will be Y, parameterized by the angle theta, C2. And then C2 will be Rx phi C3, C3, C2. C2 will be C3. Okay, so what I can do is I can start eliminating C1. So I just sub in this. I sub the C1 here, sub this C2 here, and then I can end up with an expression which relates C0 with RZ psi, RY theta, Rx phi, C3. Okay, so C0 is, this is my grand rotation matrix, C3. This is, by the way, the one in body frame, which remains with the body and rotates with this. This is the one in the fixed frame. This is a vector in fixed frame, and R is the rotation matrix. The other way you write this in general would be R in, remember there was 0, which indicates the world frame, R, which is the rotation matrix, and small r, body, is the body frame. So this is basically how we've always seen this turned out to be, right? We have position in body frame. So R0 is position in body frame. Sorry, R is position in fixed frame, my bad, fixed frame. R body is position in body frame. And capital R is the necessary rotation matrix. So you can relate how rotations, how an object is going to be oriented when you rotate it in three-dimensional space using this notation, which is the same in 2 dimensions, except that R would be less complicated. Okay, so one last thing before we stop, you can actually expand this out, and I'll write it down what it is. It looks pretty ugly, but I'll just write it down. And I would never recommend trying to write this by hand. You just want to use a symbolic calculator to do this. And I taught you how to use symbolics some time back. So that's the last thing. So let me write this down. So R is RZ psi, RY theta, Rx phi. Okay, so I did not do this calculation by hand. Clearly, I used symbolic Python to do it. Cosine theta, sine psi, minus sine theta. So this is my column 1. Then we have cosine psi, sine phi, sine theta, minus cos theta, sine psi, cos psi, cos phi, plus sine phi, sine psi, sine theta, cos theta, sine phi. Need a lot more space. Okay, one more column. We're done. Sine phi, sine c, plus cos phi, just running out of space. Cos phi, cos psi, cos phi, and I just set it up sine theta. Okay, second one is cos phi, sine psi, sine theta minus, my God, cosine psi, sine phi, and then cosine phi, cosine theta. Okay, so this is one expression, obviously, and then this one is another one. Let's change this color to another one. So that is how it looks.